it's about solutions with concentrated vorticities in 2D and 3D Euler equations. So let me introduce the subject. It's a very classical one. I will consider first the Euler equation in 2 dimensions in entire space, which is, as everybody knows, this problem here. When written in vorticity, not the equation for the velocity field, but the equation for the vorticity, which is a scalar function satisfying this transport equation, where the transport is due to this potential here, where psi is the inverse Laplacian of omega. So this is a non-local transport equation. So it's a mix between transport and elliptic, and the Newtonian potential in entire R2. Well, I take it to be this guy, right? A convolution with the fundamental solution. And this notation pair from now on for me means this, okay? Okay, the velocity field, by the way, of the fluid is driven by this equation, would be given by the gradient perp of psi, which is nothing but this integral here, this slightly singular integral. And omega, the unknown here, is the vorticity, so it's a measure of the tendency to rotate of the fluid, which is, since we are in the 2-dimensional case, we can identify that with a scalar, which is nothing but this, this quantity. No? Okay. Concerning existence and uniqueness of solutions, this is a delicate subject. I mean, it strongly depends on the class of initial conditions that we take. However, existence of solutions in L infinity is well known. In this class, there is no blow up. And if you start with an initial condition in vorticity, which is uniformly bounded, then the solution remains uniformly bounded at all times. And is well defined as a weak solution or distributional solution of this problem. Not only that, it is also known that if this initial condition is regular, then the solution is also regular. So you don't develop singularities in any sense if you are in, at least when you are in entire space and you are in the class of bounded things. Okay, so this is a well-established theory, known since 1930s, and especially the most complete result of this type is by Udovich in the early 1960s. Let me comment something that is kind of elementary. However, it's a very nice situation for the Euler equation, is that whenever you have a solution of a semi-linear equation, an autonomous semi-linear equation like this, okay, a nonlinear Poisson equation of this form, then the solution of an equation of this form automatically induces a steady state of the problem V. In fact, if you let omega simply be f of psi, the right-hand side, then the second equation is satisfied, and this guy here is also automatically satisfied, because if omega is a function of psi, then you have gradient perp of psi times gradient of a function of psi. That's automatically 0. Okay? These two vectors are orthogonal, perpendicular. An example that I will pay attention, example with a name, but that I will pay special attention to, is one generated by the Liouville equation. The Liouville equation, as everybody knows, is this corresponds to exponential nonlinearity in R2, and in fact, finite mass solutions are all classified and are simply scalings of this fixed function, which has mass a pi. So this is called in the language of Euler equation, this is just called the Kaufman-Scully vortex. Let me tell you what I would like to do. This is a natural problem, a very old problem, by the way, which is that of describing solutions which have very concentrated vorticities. Very concentrated vorticities in the following sense. Essentially, what I would like to describe are solutions of the Euler system, yeah, which is described by omega psi, which in some distributional sense resembles simply a linear combination of Dirac deltas supported at a finite number of k points. If omega was exactly this right-hand side, then the corresponding psi would be the sum of fundamental solutions. So it would just be this guy. The 8 pi guy is just cosmetic, okay? However, since I will relate this with the Kaufman Schooling vortex, I prefer to use this notation. Of course, what I am talking about is regular solutions that asymptotically behave like this. Okay, these are you can make sense of these guys as actual solutions. I will describe that in a moment, and this is a very classical subject. So just to fix ideas of what we want to describe, okay? Yeah, I don't think this picture is real, okay? It corresponds to a true situation, but you can imagine what it intends to describe. If the atmosphere, the velocity field of the atmosphere is described by Euler equation and vorticity by an approximately planar situation where the geography plays no role, okay? Then you may have regions with extremely high vorticity concentrated in such a way that they are moving using certain dynamic law that we would like to describe. By the way, the reason why these coefficients here are naturally constant, okay, is because the equation preserves mass. So if you start with the mass of 8 pi kj at time 0, the mass of this guy will remain the same as time advances. Okay. So the analysis of solutions with highly concentrated vorticities, as I mentioned, is a subject with a long history. It traces back from the very origins of the theory, of the good theory, okay, for Euler equations that come from Helmholtz in 1858, Kirchhoff a little bit later, and then a little bit more recent, Roth, Lagalli, and other names. They all derived a certain formal, in our current language, formal asymptotics for the centers of these Dirac deltas. If we impose that this omega s, I will call this linear combination of Dirac deltas, if this guy is imposed to be a solution, okay, of the equation. Okay, so this is a linear combination of Dirac deltas, and so I consider that the centers are regular functions of defining some interval 0d. This omega should have been R2, sorry. Since the psi singular is in the inverse Laplacian Newtonian potential of omega s, then psi s is the corresponding linear combination of fundamental solutions centered at the point psi j, and we formally compute what the operator associated to the Euler equation becomes, to the transport problem. Say the derivative in time is simply linear combination of gradient of the Dirac delta times the derivative of psi j, and then when you differentiate this part, you obtain this double summation. And now, in this double summation, in reality, there are a number of terms that we can regard as zero. Let me explain that in the following way. The fundamental solution itself and the Dirac delta are, quote, radially symmetric functions, invariant under rotations, right? And that implies that this product, yeah, I mean, if you take gradient perp of a radial function times the gradient of a radial function, that is zero. So this product is automatically 0, and that frees us from the most singular terms in this summation. This is only formal, I insist. At the end, then what we get is simply the same summation, but with I different from j, and we have all these coefficients multiplied the gradient of the Dirac delta. So we will have a solution, quotes, of the Euler equation in case that these coefficients are all 0. Now, these coefficients being all 0 is an ODE system. It's an ODE system for the points xij, which is precisely this one down here. So it's well, so it becomes precisely this. Okay, so let me. So this is an embodied problem, right? This is an embodied problem in R2. This is the way. So the bottom line is the vortices, the asymptotics vortices, the actual very singular objects that are the vortices obey this particular embodied problem. They interact with according to this law, which is driven by Green's function of Laplace. On the other hand, in reality, the solution, an actual solution, which is a configuration of the atmosphere, is not singular. It's a regular function. In fact, at the center, right, of the typhoon, we should see velocity 0, right? So you see a smooth function. If you want very sharp, but smooth. And it is not really obvious that the Euler system will describe or will have solutions that behave in this form. Yeah? And this is the type of question I would like to address. We're definitely not the first ones in addressing them, but maybe in the sense that I will describe, perhaps yes. Okay, so here is the system. I will call the system K from now on for Kirchhoff. And so the question is, are there true solutions, smooth, of the Euler equation V in vorticity form, whose vorticity is highly concentrated around a finite set of points, evolved by the dynamics approximated by a dynamic law approximated by this guy. This is what I would like to do. In other words, what I would like is to desingularize the asymptotic vortices. Okay. Okay, I will describe a way to do that. Let me consider the asymptotically singular objects, yeah, with Dirac delta here and with fundamental solution here. I will put this 8 also for some, I mean, this for some reason that I will explain in a moment. Using Kaufman's Cooley vortices, yeah, you remember the vortex Cooley vortices was exactly this guy, huh? That has mass a pi. So what I will do is a regularization of the Dirac deltas using stationary states that are radially symmetric functions, highly concentrated. Okay, so what I will do is I take my Kaufman's Cooley vortex, I center it at xij and divide by epsilon, that makes a very narrow spike, right? And multiply by 1 over epsilon squared, which preserves mass. Yeah. And the corresponding, if we do this, if we do that, the corresponding psi 0 epsilon is the regularization of this, namely inverse Laplacian of this guy, and the inverse Laplacian of this guy. This is something we can check because it's just Liouville equation. Huh? It's given by this log. So it's simply log of this guy. Yeah. Okay, so this is the answers. Of course, these guys have not solutions. Why? Because say this W0 and psi correspond to a steady state, but they are centered at time-dependent things. So there will be no solution precisely of this form, except in the case that you have just one spike and this center fixed. Yeah. On the other hand, we observe the following. As we expected, right, these regularizations, these epsilon regularizations, respectively converge in distributional sense to these two things. Here there is an A pi missing, sorry about that. Yeah, I think this one is correct. And no, this is just to emphasize also this property that if you take the velocity field, yeah, the velocity field, the density of the velocity field, namely this quantity, and you normalize it by log epsilon, then you approach a distributional limit, which is sum of Dirac deltas centered at those centers, at the corresponding points. Okay, so we have this scenario. Then what I will tell you something about the result that we have, which is the following. Essentially, let me tell you this. If you consider a solution of the Kirchhoff system, Kirchhoff-Roth system, which is this one, and you consider the associated regularizations omega 0 epsilon and psi 0 epsilon, then we will find an actual solution, a true solution of the Euler system, which differs little from that pair, okay? And we can give an exact account of, well, a pretty exact account, I should say, of that difference. Yeah. And that's our result. So this is what we are looking for, okay? So this intends to be the graph of the spikes given by W0 epsilon. Yeah. Okay, so this is the result a couple of years ago by Juan Davila, Mónica Musso, Junchen Wei, and I. We proved the following. We proved that there exists an actual solution. No, okay. Given a solution without collisions, okay, we want that it be regular solution, right? Given a regular solution, namely collisionless solutions of the n-body problem K, in a fixed time interval 0t, there exists a solution of problem V of the Euler system with the following form. This solution, the omega epsilon, can be expanded as the corresponding sum of the Scully vortex, Kaufman-Scully vortices, plus remainders phi and psi, where the phi can be bounded in the following way. Can be bounded by a small power. I mean, you have a number sigma here less than 1. You can bound it as by a power of epsilon times the bubble, times the main term of the bubble. So this phi is small compared with the main gap. Yeah, even you can measure it precisely what this power is. Yeah? In reality, if you go a little further with the method that I will tell you later, in reality, phi can be proven that it is even uniformly bounded in an infinity, but we will not. I will not elaborate like that now. However, what you can say is that this psi, which is the inverse Laplacian of phi, in reality is quite small. Okay, the solution phi psi is of size epsilon squared, and the gradient goes like this. Okay, so in particular, I have the omega epsilon and the psi epsilon satisfy these inequalities. There is a previous result, a result in 1993, very nice result by Marchioro and Pulvirenti, in which they build distributional solutions satisfying an asymptotic property like this. The method was not difficult. They just analyzed the initial value problem and found some integral estimate of the solution to prove the distributional convergence. On the other hand, they found not really fine information around the vortex, around the place where the vortices are. Okay, so that's the difference with our result. In particular, they were not able to decide what happened with the velocity field, with the asymptotics of the velocity field, even in the distributional sense. Okay, now concerning ingredients in our construction, let me tell you how it goes. We regard this as a singular perturbation problem in which the singular perturbation parameter is that epsilon. We fix an interval of time and a solution of the problem.
Pero sí, hace unos minutos, tipo acá por el 249, Guillermo tenía.
Sorry? Okay, no, that was the question or no? Okay, probably.
I guess you can go ahead, Manuel. It's okay.
Yeah. Okay, so what we work out is an improvement of approximation in powers of epsilon for the solution. What I mean is that we find a very accurate approximation using a method that I will describe in a moment that actually alternates the use of elliptic and transport equations. And later we set up the full problem as a coupled system of inner problems that describe what is happening near the singularities, and an outer problem which is much more regular and essentially a regular transport equation. Yeah, this type of approach we sometimes call the inner outer gluing scheme. I will tell you what it is in a moment. Finally, in order to solve the true problem, we need the method we use is a priori estimates. And these a priori estimates make it applicable degree argument, the Leray-Schauder degree argument. I mean, this is kind of interesting because this problem doesn't seem to be good for employing Banach fixed point theorem. However, the a priori estimates and degree work, at least to prove existence. Okay, how does that go? Say, concerning the improvement of the approximation, let me consider the basic object that is the Kaufman-Scully vortex. Then this approximation which is given by this guy here, this is what a way in which I write the psi 0 epsilon, can be written in this term, in this way, in terms of this function. And in fact, this variable x minus ij over epsilon is the variable that describes naturally what is going on near the point xij. We want that the Euler equation is satisfied. So what I want is that this operator in omega psi is 0, right? Okay, I will do an ansatz. I will make an ansatz for a true solution. Yeah, I would like to find a solution. Yeah, that is a perturbation of a small perturbation of this guy, and the corresponding omega, the vorticity, will be the Kaufman-Scully vortex scaled plus a remainder that naturally again I take it of this form. The variable y is this scaled x minus ij of t, so it's moving, right, and scaling epsilon. Okay, I will substitute that into the operator and see more or less what comes out as an equation for psi and phi. If I substitute it inside the corresponding system, I get this equation here. So this is what I would like the pair phi psi satisfies. On the other hand, the psi 0 epsilon can be expanded in this way, yeah, kappa j times the gamma 0 of the Kaufman-Scully vortex, plus a function phi of x, which is nothing but this guy. I am analyzing what is going on near a point psi j. Yeah? So y say bounded, large but bounded. And then phi is precisely this linear combination. So I can compute then what comes out of this expansion, and use the fact that I am solving approximately, right? I am solving approximately the system psi j dot equal to this. This is a way to write the Kirchhoff system. So I substitute that here, yeah, and then it turns out that this quantity here can be expanded in this way. A simply gradient pair of gamma 0 plus a remainder, where this remainder is quadratic, or precisely is the epsilon square y square. So when I substitute that expression in the system, what I get is this. It's kind of simple, but then you see how the problem looks like in terms of this small perturbation phi m psi. Let me write f of u to be the exponential, and u0, I remind you, u0 is simply the exponential of gamma 0. This is the Liouville equation. Yeah? And what we find is that the error associated can be written as this operator, which is linear in phi psi, but psi is simply inverse Laplacian of phi. So this is a sort of transport non-local equation. So actually, it is a transport equation for this object. And there are noises, right? Remainders that are given by this quadratic term, which is the only thing nonlinear that actually comes, plus these other smaller terms that I will analyze in a second. The first error term, which is what you find when you plug in here, in this expression, you plug in simply phi psi equal to 0. It is just gradient perp of r times gradient u0, which is what form does this have? R, remember, is epsilon squared y squared. So this is epsilon squared y times gradient u0, which is 1 over rho to power 5. So this is what you see. Okay, epsilon squared times y to power minus 4. And we will get, therefore, a reduction in the error, by solving something which is simply an elliptic equation, which is just this part of the operator plus this equal to 0. The other guys will a posteriori be smaller, which is natural. These guys come with more powers of epsilon. Concerning how do I solve this equation? You can recognize perhaps what is down here. This is just the linearized operator associated to Liouville equation around the standard bubble gamma 0. We are able to solve these equations. If in general you can solve these problems, you have right-hand sides which are in Fourier modes that avoid mode 0. Okay, that avoid mode 0 in Fourier series expansion. After sufficiently improving the approximation, say we actually iterate this in order to get better approximation, but that is only good near the vortices, not really far away. To take care of the part far away, we have to argue in a slightly different way. We will actually we iterate that with the transport part of the operator in order to take care of the outer part of the outer regime, and we put that back and then iterate. Okay. At the end, if you are careful enough, you end up with an error of this one: epsilon to power 5 times rho to minus 3. Why I was so interested in getting epsilon to power 5 and not smaller? The reason the reason is simple. The reason is because this E is like epsilon squared, right? When you solve for phi, in general, you expect to lose epsilon squared. So if you start with epsilon to power 4, say that you are only up to epsilon to power 4, then you divide by epsilon squared, you get epsilon squared, right? And in the phi, and then you have a quadratic term, and that quadratic term will come with epsilon to power 4 again. So you don't iterate. This is the reason why you want to get a higher precision. A key technical element is the following: is that this linear equation here, if you assume a priori that the phi satisfies these two conditions, center of mass in a large ball, 0, and mass 0, if you assume those two things, then you have a weighted to estimate, which is precisely given by this. This weighted to estimate takes into account space decay of phi and L2 norm, of course, but you also lose some power of epsilon. Okay, and this is the way eventually you use this and some regularity stuff and so on to attack the problem with the fixed point scheme. Here it should say epsilon to -4 because I'm talking about phi square. Sorry, that's a misprint. Okay, let me tell you, this is an interesting problem. It looks very similar, but it turns out to be very, very interesting. The surface quasi-geostrophic equation. The surface quasi-geostrophic equation is an object very similar to the Euler equation. The only difference is that here, rather than inverse Laplacian, you take the inverse of fractional Laplacian. Yeah? Also expressed in convolution way. The inverse Laplacian, the inverse fractional Laplacian S is given as it is well known, right, by this formula for the suitable constant CS. And then the question is, of course, the same. I mean, can we find solutions with highly concentrated vorticities that evolve according to some asymptotic law? Well, if you do similar computations to what I showed you at the beginning, you end up now with this system. The only difference between this system and the one for Euler is the power. Okay, when the power for Euler is S equal to 1, so you get the 2 here. So it's again an n-body problem that becomes more singular as S goes down. Yeah? So a result that we found with Antonio Fernandez, who was my postdoc until recently, was the following. If the fractional power S is bigger than or equal to 9/10, I mean, we were working very hard to get 1/2, but we have not been able to. In fact, it's already quite a lot of work to get to this number. The truth is that the true number we get is a little bit smaller. It's 0.887. This is why I put it bigger than or equal here. And what we are able to get is that if you consider a collisionless solution for this embodied problem, then you can find a solution of the generalized SQG, the surface quasi-geostrophic equation, such that this approximation holds. So it's a very similar. It's exactly the same result, but the work necessary to prove this, even if you try to use the same lines, is considerably harder. And maybe something to mention is that we found this result with Ao Wei, Juan Davila, Monica Musso, and Juncheng Wei. This was recently published, in which we found a traveling wave solution for the SQG. Yeah, for this problem. In fact, we were able to do it for any positive S. Yeah? Of course, those are special solutions, and the problem reduces to something that is actually elliptic. Okay.
Sorry, I have one question. So,
yes.
Yeah, sorry. Yeah, so for both KS and the K here for this ODE, do you know for general initial data, would this ODE stay regular for all time t, or when t go to infinity? Can you?
That's a very good question.
Yeah.
Yes, you can find very simple examples when that happens. I can give you one. Okay. One is that you consider the vortex pair, right, for instance, is the classical solution to it. Yeah.
Yeah.
And you can take two vortex pairs traveling in the opposite directions.
Oh,
you can actually
right,
find
I understand.
a solution. Huh?
Yeah, but I'm asking the opposite. So can you show that for all initial data, this ODE will be regular, just no singularity for all initial data?
No, it is possible that you get collisions.
Oh,
that is possible,
yeah,
but the regime is different in that case. Say that's a very exciting problem. Huh? Getting the two asymptotics when you have collisions, but this is something that we don't know how to do yet.
Thank you. Yeah, thanks. Okay, thank you.
Well, anyway, concerning the SQG scenario, you had already recent results of the same type of Marchero-Pulvirenti, but something that is quite bothersome actually is that you don't have a simple theory like Udovich theory for the generalized quasi-geostrophics. Essentially, you have no idea if you have existence for at all times for regular solutions. And I mean, people don't know, but I think people tend to believe that solutions could be regular up to 1/2, but it's not. This has not been proven. It's far from being proven. Okay, at this moment, I think, and so the lack of regularity of the transport term is an essential issue. This is why we have to work hard in order to construct a solution. We're constructing a solution. Yeah. So in particular, we need a very high accuracy of the approximation. We can, even in some situations, we need arbitrarily large order in powers of epsilon, or I mean, very large power of epsilon. If S is close from above to certain limiting value that we end up finding 0.887. We strongly believe that the result should be true up to 1/2, but we don't have the proof yet. At the beginning, we thought it was up to 1/2, but no, there was an obstruction. Anyway, let me comment you something about the three-dimensional case. The three-dimensional case is an exciting question called the vortex filament question. Not just vortices. Vortices are points in R2, but in R3, they are lines, right? Like, I don't know, like this sequence of tornadoes again, but now we have to think of them in 3D. Or more realistic, I mean, this is a true picture, okay, of a smoke ring. And rings traveling, right? It's a classical subject. I mean, these objects are mathematically known for many, many years. In general, the question is, and until today, widely open, is the existence of solutions with highly concentrated vorticities near curves. Yeah. The formal dynamics law is known and in relative times not for such a long time. And the fact that that holds for true solutions is called the vortex filament conjecture. And the analysis of these things comes from Helmholtz and Darrios and Levi-Civita. Darrios, in his thesis with Levi-Civita, actually found in 1906 the true asymptotic law. Let me tell you something about that law. We consider the Euler equation in a string vorticity form. Now in R3, which is these more complicated objects, these omega and psi are now vectors. Okay. So what we want to find are solutions with vorticity concentrated on a time evolving curve parameterized by arc length. The vortex filament dynamics can be described in the following way. After some computation, not trivial at all. Yeah, it turns out that if you consider solutions that look like this, like Dirac deltas now along curves, yeah, times this is the measure. Okay, this is a measure value thing, but it's smooth, right? I mean, here you have the tangent vector to a curve evolving in time. What I would like to find now is the evolution law for the curve. It turns out that if you scale the time further using this log epsilon factor, and a very concentrated solutions concentrated in a tube with epsilon for the as initial conditions, then you formally end up with this law for the thing. I mean, for the evolution of the curve. And this law is called the binormal flow, and it has attracted a lot of research also in recent years. And this is the binormal vector of the curve. Yeah, okay, using this standard notation for geometry of curves. The vortex filament conjecture is that given a solution of the binormal flow, you can find a true solution omega epsilon that behaves like this. Once you scale with the log epsilon, you end up approaching the dynamics of the curve in this form. It is, of course, natural to look for a solution of the form where you concentrate the Dirac delta using, again, the Quoc-Hung vortex. And this statement is only known for very special curves. And in fact, I can tell you which ones. The one is a thin vortex ring. The thin vortex ring is something traveling with constant speed vertically, okay, like that, and a helix. These are two special solutions of the binormal flow of curves. The nice thing is that you can reduce the problem using the suitable answers to an elliptic equation. Yeah, and in the case of helicoidal symmetry, in fact, we have recently found the corresponding solutions. I will not tell you details, but it comes from solving a problem singular perturbations, a singular perturbed elliptic equation And well, so this is a result again with Juan, Monica, and Jun Cheng, in which we find for this Liouville equation something concentrated at a rotating helix, like the one I showed you before, which is solution of the binormal flow. Let me tell you that the case of the ring, okay, corresponds to a solution of this form with this special symmetry, at least in the no-swirl case. And these are called vortex rings, yeah? And they are known for a long time. In particular, there is the classical work by Frankel in the 1970s, and there were even before. Let me tell you quickly, okay, about this very interesting phenomenon, okay, which is we have been able to describe recently. Helmholtz in 1958 predicted the way that two coaxial vortex rings interact, okay? And essentially one goes, the two of them are traveling at an approximately constant speed to the right, okay? But then it turns out that one is going after the other, it crosses it, and then the velocity in reality is connected with the radius, and this radius is oscillating. So you see these alternating rings motion in this alternating ring motion. Well, you see more or less what I mean. In fact, in order to describe it, if you don't mind, let me show you a picture. Actually, rather than a picture, this is a movie that I actually found today by Eduardo Alvarez. This is by, in fact, I found it just by chance. You have many, if you go to YouTube or other systems, you find many, even experiments and numerical experiments concerning this vortex ring motion or the leapfrogging motion. And let me tell you how it goes. This is what I mean, okay? What I meant to describe by words, yeah? These guys are traveling to the right. Well, eventually everything collapses, okay? No. You cannot see that for a very long time. I mean, not indefinitely. Okay, let me tell you in this situation what we have been able to find. Just a second. Yeah, here it is. So what we have been able to find is a true description for this motion. The nice thing is that since these things are circular, you can restrict yourself to a two-dimensional, to a situation with two variables. Okay, and if you write the Euler, the corresponding Euler system without swirl, you eventually find an answer that looks again like the Kaufman-Scully vortices. And now essentially the thing is the following: if you find for the centers of the vortice of these rings, okay, these are the radii of the rings actually, and they alternate in a periodic manner, okay, somehow. If you have a solution of this system defined in an interval 0t, then you can find a true solution that behaves in this way. Okay, thank you very much for your attention.